Please don't go.
So I have in front of me right now Form A from the conservation quiz that you guys took yesterday. If you don't have Form A, if you took a different form, you might have to skip around to find the questions because I'll be going in order of the ones on my screen. But we're going to go over this, and then if you have questions as I'm going over it, please ask. You have a test tomorrow. I don't want you to make the same mistakes on the test that you made on the quiz, although I will say overall the quiz grades were really good, especially in this class period. So let's go ahead and take a look at these questions. We'll go through them one at a time. And if you have questions, please make sure that you ask those because your test tomorrow, you're going to need to know not just this stuff, but also, potentially some other things as well for that free response. We'll get to that later on. After we're done with this, I'll talk a little bit more about the free response tomorrow. Number 1 on Form A is about a soccer ball. So again, if you don't have Form A, please look for this question. It says, a soccer ball collides with another soccer ball at rest. The total momentum of the system, and your choices are, is 0, increases, decreases, or remains constant. And this goes back to a definition for the law of conservation of momentum. If you have a collision between two objects, the total initial momentum of your system will equal the total final momentum of your system, meaning that the total momentum is conserved. It does not change. And so the total momentum of the system will remain constant. The answer to number 1 is D. Only one person missed that. Hopefully, if you did miss it, maybe you misbubbled, I don't know. But make a note or a mental note or whatever, but you guys need to know conservation of momentum. It's one of the main topics for this unit. Are there any questions about number 1? Okay. Number 2 says 2 skaters stand facing each other. One skater's mass is 60 kilograms and the other's mass is 72 kilograms. If the skaters push away from each other without spinning, what's going to happen here? And your answer choices are their total momentum doubles, their total momentum decreases, the 60 kilogram skater travels at a lower momentum, or their momentum values are equal but opposite. And that is your answer. Their momentum values are equal but opposite. Okay, this still goes back to law of conservation of momentum, but this particular example is an example of a recoil type of collision, where you have 2 objects that start out together and there's some type of force that causes them and pushes them away from each other. Most of our recoil examples that we've looked at have been like cannons firing cannonballs, or the spring that causes the carts to move apart, like what you saw in the RA. But it could just as easily be something like this, where you have 2 people pushing off of each other. And so that answer here, because they started out at rest and their initial momentum was 0, their total final momentum must also be 0, which means that if one of them has a momentum of, let's say, positive 100, well, the other one has to be negative 100, so that the total is 0, so the total remains the same, so that it follows the law of conservation of momentum. And so their momentum values are equal but opposite is the answer choice you should select there. Are there any questions about number 2? All right. Number 3. 92% of you guys got right. It says a 65 kilogram cannon launches a 150 gram cannonball horizontally at a speed of 32 meters per second. With what velocity does the cannon move? Okay, and if you look at this, this is a calculation of a recoil type of collision. We just looked at a recoil in the previous question, but now we're going to do some math with it. Okay, and so when you look at these, you're going to want to start by labeling the information that you're given. And you need to have 2 objects. I'm going to go ahead and number them 1 and 2 like we have been doing. And so I'm going to call my cannon object 1, and I'm going to say the mass of object 1 is 65 kilograms. I just picked that one to be 1 because it was listed first in the question. Okay, it doesn't really matter. I know that the initial velocity of my cannon is 0. Before it is fired, it's not moving. Okay, and then object 2, M2, is my cannonball. It has a mass of 150 grams. I can't use that number without first converting it. If you missed this question, that very well could be why. Okay, and so I don't want 150 grams. I need to know how many kilograms that is. I have to divide it by 1,000, and I'm going to get 0.15 kilograms. Again, its initial velocity before it is fired is 0. It's not moving yet before it is fired. Okay, and then afterward, again, with these you're going to have a before and an after. After it is fired, I'm trying to figure out how fast my cannon is moving. That's the question. What is the with what velocity does the cannon move? Okay, but I do know how fast the cannonball moves. Its final velocity is in the question, 32 meters per second. And so from here, I can solve and figure out how fast object 1 is moving. Note their masses aren't going to change. I did not bother writing them down twice. Okay, so from here, we're going to use that equation that we've been using in class. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That's the equation that we've used for all of our conservation of momentum, and that's exactly what we're going to use here for this type of collision. So let's go ahead and plug in. Now, my initial momentum of my system will be 0 because both of the initial velocities are 0. There was a shortcut for recoil, and that was just saying this, 0 equals, because your total initial will be 0 on the left-hand side. On the right-hand side, though, I do have a velocity. It's not going to be 0, and so my first mass, M1, 65, has some velocity. That's the one I'm looking for. And then my second mass, 0.15, has a velocity of 32 meters per second. Okay, and so that's what I get when I substitute my numbers in. And we need to go ahead and solve what we can here. So let's go ahead and multiply 0.15 times 32. And that's going to give us 4.8. Again, I'm trying to solve for this, so I'm going to subtract that 4.8 from both sides, and that's going to give me negative 4.8 equals 65 times V1F. From here, I need to divide both sides by 65, and that'll give me my final answer. Note that it will be negative, which makes sense. We just talked about that in the previous question. With a recoil collision, one of the objects goes forward and one goes backward. My velocity of my cannonball was forward. It was positive 32. So it makes sense that the final velocity of my cannon is negative, and it's specifically negative 0.074 or 38 is what it says up here. And so the answer that you should select for number 3 is answer choice B. As I said, 92% of you got this right, but does anybody have a question about the math? Okay, then let's go ahead and take a look at number 4. Number 4 says, a freight train rolls along a track with considerable momentum. Consider a similar train rolls at the same speed, but with twice the mass. The second train's momentum would be. Okay, so here you're really just looking at the relationship between mass and momentum. And you can see that if you just look at the momentum equation. The momentum equation, again, is P, momentum, equals mass times velocity. It says here that the velocity is the same speed. And so the question is, how does doubling this mass affect this? And if you double your mass, you will also double your momentum. They are directly proportional to each other. And so that second train's momentum would be doubled, and that is answer choice E for number 4. Not a single one of you missed that in this class period. So everybody got that one right, which is great, because we should be doing good with these proportional reasoning questions. Questions about number 4, though? All right, numbers 5, 6, and 7 on mine all go with this scenario about 2 vehicles, a semi-truck, and a small car colliding. Okay, so again, if you don't have Form A, look for that scenario. There are 3 questions here. We're going to start with number 5, which of the 3 was the most missed question. Okay, not on the whole quiz, but of these 3, 5 was more missed than 6 or 7. Okay, number 5 says, which of the following statements is true regarding the change in momentum during the collision? We've talked about this a couple times now, and it goes back to our definition. Guys, if the total momentum of the system has to remain constant, then that means that the change in momentum of the car and the change in momentum of the semi-truck when they collide have to be equal and opposite to each other. If one has a change of negative 100, the other one has to have a change of positive 100, so the total stays the same. So the total is 0 change. Okay, and so it's just conservation of momentum. Number 5 is C. The semi-truck and car experience the same change in momentum. I would like it better if it said the same magnitude of, okay, because it's technically opposite sign, but it's the only answer here that makes any sense. Okay, so the answer you should have selected for number 5 is C. Some of you are still getting thrown off and thinking that the car is going to have a greater change in momentum because it's smaller, and it doesn't. Now, it does affect its change in velocity, which is the next question. Okay, so number 6 says, which of the following statements is true regarding the change in velocity during the collision? And we talked about this in class as well, multiple times. Okay, but we looked at this. We said if the change in momentum has to be the same, which it does, then that means that the object with the smaller mass has to have a larger change in velocity than the object with the large mass, which would have a smaller change in velocity, so that the two are equal. Because they have different masses, they absolutely have different changes in velocity. They don't have different changes in momentum, but they do have different changes in velocity. Because in order for the change in momentum to equal the change in momentum, that has to be true. Okay, and so the smaller object will have a greater change in velocity. It will also have a greater acceleration. We talked about that as well. Okay, and the smaller object is the car, and so the answer to number 6 should be B. The car shows a greater change in velocity. Questions about number 6? Okay. Number 7. Which of the following statements is true regarding the forces during the collision? And I am very happy to report that every single one of you got this right. Nobody forgot Newton's third law. I thought it was going to happen. I thought somebody was going to forget it. In my other classes they did. But you guys, every person in this room got Newton's third law. For every action, there is an equal and opposite reaction. Those forces are equal and opposite. It is a force pair. Okay, so that's what you should have selected. For number 7 is answer choice C. The semi-truck and car experience the same magnitude of force. Again, I prefer the word magnitude in there, but again, it's the only one that makes any sense because it is equal and opposite. All right, any questions about 5, 6, or 7? Like I said, you guys did really good with this overall. I think y'all's average was like an 86 or something. It was really high. All right, number 8. Number 8, some of you had trouble with. I don't know if it was your most missed. It is not the most missed, but it was tied for second most missed question. So if you missed one, there is a chance it could have been this one, so make sure you're listening. It says, a duck and chicken are running straight toward each other. The duck is going 7.50 meters per second and has a mass of 6 kilograms. The chicken is going negative 8.70 meters per second and has a mass of 4.30 kilograms. The two vicious animals collide. After the collision, the duck bounces backward at 2.10 meters per second. How fast does the chicken move and in what direction? Guys, I would start with a picture. You don't have to draw a pretty picture. This can be your duck. It can be a box. If you want to draw an actual duck, you can. But I'm going to say that this is my duck. It's moving. I'm going to go ahead, since it says it's positive 7, I'm going to go ahead and draw that to the right. I'm going to call this forward. 7.5 meters per second. It has a mass of 6 kilograms. Okay, my chicken is moving toward my duck with a velocity of negative 8.7 meters per second, and it has a mass of 4.3 kilograms. Okay, so that's the information that I have for before the collision. Again, when we draw these pictures, we really want a before and after. So that's before. Let's look at after. It says, afterward, the duck bounces backward. This was my duck. If he bounces backward, that means he's now going this way. okay, at 2.10. I'm going to call that negative 2.1. It's backwards. It's the opposite direction. It needs to have the opposite sign. Okay, so that's his, and he still has the same mass. And the question is, what happens to the chicken? Which way is he going? How fast is he going? We don't know. That's what we're going to solve. And again, we're going to use conservation of momentum to do it. If you have a collision like this, that's what you're going to do. You're going to use that equation, m1v1 initial plus m2v2 initial, that's the total initial momentum of those objects, equals m1v1 final plus m2v2 final, that's the total final momentum of those objects. So let's plug in those numbers. m1 is 6, v1 is 7.5, m2 is 4.3, v2 is negative 8.7. We're going to set that equal to 6 times my VF for the object 1, negative 2.1, plus 4.3 times my final velocity of object 2. So that's my substitution step. Now I just have to solve. So we're going to go ahead and solve the entire left-hand side of this equation. So 6 times 7.5 plus 4.3 times negative 8.7. Make sure you put that negative sign in there. That whole side is 7.59. So that is the total initial momentum of the objects, which means it is also equal to the total final momentum of the objects because the momentum is conserved in a collision. So let's go ahead and figure out what 6 times negative 2.1 is. Negative 12.6 plus 4.3 V2F. From here, algebraically, again, do not add these. They are not like terms. We're going to move this over here. So we're going to add 12.6 to both sides. So 7.59 plus 12.6 is equal to 20.19, and that equals 4.3 V2F. Notice my negative sign is gone. I already know which way the chicken's going to go. He's forward. It's a positive number. Now we just have to get the number. 20.19 divided by 4.3 gives me 4.69, and it keeps going from there. But it's, again, a positive number, so it's going to be 4.69 meters per second forward. That is answer choice B for number 8. Questions about this one? I don't know if you all got thrown off by the forward and backward piece or the math, but just be careful with it. If you draw a picture, you can see it pretty easily, okay? And hopefully that helps you see that this needs a negative sign in front of it. And again, if you have questions, please make sure you're asking them, guys. I don't want y'all to miss these on your test tomorrow. All right, this is number 9 on Form A. So again, if you don't have Form A, you were looking for this image of a pendulum. 88% of you guys got this question right, so that's really good. It says, imagine a frictionless pendulum. The pendulum bob starts from rest at the shaded position labeled bob and swings on its rope towards positions A through E. What is the highest position the pendulum bob will reach on the opposite side of its swing? And you need to read your choices carefully because they're not A, B, C, D, E. I mean, A is not a choice. Okay, your choices are position B, C, D, E, or it depends on how much the bob weighs. Okay, well, we looked at this in class. We watched a video with the pendulum. We talked about it as well. But we know that this pendulum is going to convert gravitational potential energy to kinetic energy and back to gravitational potential energy again as it swings up on the other side. But we also know, according to the law of conservation of energy, that it can't swing higher than it started, which means it's impossible for it to reach point E. In fact, if it's frictionless, which it says it is, then it should reach the exact same height that it started, okay, where it started. And so it started here. On this side, it should reach here. That's D, position D. That's not answer choice D, though. Hopefully you read them carefully. But it should swing up here and then just go back and forth, theoretically forever, because there's no friction. Okay, the answer you should have selected position D is actually answer choice C. Okay, so that's what you should have put for number 9 is C. Hopefully y'all read that carefully. I know in my last class I had some people that missed it because they bubbled D because they were trying to put position D, not because they were trying to put position E. So hopefully that didn't happen to you, but if so, please don't do that tomorrow. Read the choices carefully. Did you do that?
Yeah.
You're not the only one. All right. Let's go ahead and take a look at number 10, which is a different pendulum. Number 10 says a pendulum is released and allowed to swing back and forth. The pendulum bob swings to a shorter and shorter height each time it completes a swing until it finally stops moving after a couple of minutes. Based on the information provided, this system can be described as. So this pendulum is different than the last one. Because the last one, we talked about the fact that because there was no friction, it should swing all the way back up to that same height, and then it would just go forever. This one describes a pendulum that gets to lower and lower height each time, and the only way that's going to happen is if you have energy dissipated from the system. Okay, meaning that friction causes your pendulum to lose some of that energy, and it has a little bit less gravitational potential energy and a little bit less kinetic energy with each swing. That is what an open system is. This is just a definition. The answer to number 10 is A. The system has to be open because energy is leaving that system. We have dissipated energy transferring to the surroundings. The answer to number 10 should be A. Are there any questions about number 10? All right. Yeah. Number 11 has this boy using a slingshot. Okay, let's see how we did with number 11. Last period they did pretty good. All right. Second. Sorry, I closed the thing on accident. There it is. 85% of you got number 11 correct. Okay, it says the boy pulls back the slingshot band, displacing it 0.095 meters from its resting length in image A. If the spring constant of the slingshot band is 1,741 newtons per meter, what is the velocity of a 0.043 kilogram rock when it's launched in image B? So this is a situation where we have energy transforming from one form to another. Specifically, we have elastic potential energy because it describes him stretching the band, and it gives us information about the spring constant and the displacement of the band. So we know we have elastic potential energy initially, and we know that because of this elastic potential energy, this rock is going to move. It's going to give it kinetic energy, and those two should be equal to each other. Okay, unless there's mention of some kind of dissipated energy or heat produced or something like that, which there is no mention of here. Okay, so they should be equal to each other. So you have to start by writing an energy transfer equation. But the question doesn't give us, hey, here's the elastic potential energy. It gives us a spring constant. It gives us a displacement. It gives us a mass. We need the variables. EPE is 1/2 kx squared. KE is 1/2 mv squared. That's what you're going to substitute into, but you have to be able to write the equation. If you can't write it, you obviously can't get the answer, unless you just happen to guess. So let's go ahead and substitute in 1/2. My spring constant value is 1741. My displacement is 0.095 squared equals 1/2. The mass is 0.043, and we're looking for that velocity. Okay, so that's my substitution step. Okay, let's go ahead and solve the entire left-hand side of this equation. We're going to do half of 1741, and then multiply that times 0.095 squared. Okay, and that is 7.856 equals 0.043 divided by 2, or half of that, which is 0.0215 v squared. Okay, from here we're going to divide both sides by 0.0215, and then we're going to have to take the square root. Okay, so the square root of that number that I got, sorry, I'm not used to using this Inspire. Is 19.1156. It keeps going from there. But that's answer choice B for number 11. Again, 85% of you got that one right. Are there questions about number 11? All right, let's go ahead and take a look at numbers 12 and 13, which both go with the same image. So this is what you're looking for. Sorry, this is what you're looking for numbers 12 and 13. It is a ball rolling down a frictionless track. It calls it a roller coaster, but it does say neglect friction up here. And so number 12 says, at which point on the roller coaster above is kinetic energy greatest? Okay, if you have a frictionless roller coaster or track, whatever, okay, then that means that you're going to have conversion of energy between gravitational potential to kinetic. And the point where you have the least gravitational potential energy is where you will have the most kinetic energy if it's just exchanging between those two, which means all you're looking for here is the lowest point, because that should be the point at which it's moving fastest. And that is going to be 0.6 down here. The answer to number 12 should be D. Again, 92% of you guys got that one right. And nobody missed number 13. My last class did, but nobody in here did. It says, at which point on the roller coaster above is the total mechanical energy the greatest? I'm glad nobody fell for it. Your total mechanical energy remains constant throughout. That's the whole point. Okay, if it's frictionless and there's no dissipated energy, you should have the exact same amount of total mechanical energy. You did this in the RA, part 1 of the RA. Your entire right-hand column for total mechanical energy was the same the whole way down because there was no friction in those calculations. Same idea here. And again, the answer to number 13 is E, equal at all points. And again, nobody missed that one. All right, number 14, though, was one of the most missed questions. It's the second most missed question, which I was surprised by. So I'm assuming it's because maybe you didn't read it very carefully. But let's go ahead and take a look at it. It says, which of the following sets of pie charts correctly matches the energies in the situation shown below, where the box slides down a frictionless elevated track and comes to a stop by compressing a spring? So there are 3 different points shown here, and you're going to draw 3 different pie charts that correspond to them. Okay, now first thing first, at the top right here, it shows a box that is moving. It's already moving. There's an arrow there showing that it's moving. There's also letters up here that say V is greater than 0. It's in motion. Yes, it has height, but it also has kinetic energy, which means I already know my answer. I can eliminate C and D right off the bat because they don't show any initial kinetic energy, and yet my picture does show initial kinetic energy. I don't have elastic energy here, so it has to be A. That's going to be our answer, but let's talk about the other graphs. So you have both gravitational potential and kinetic here. At this point, you still have some gravitational potential. It's not to the bottom, but the kinetic should be a greater portion of that pie, and that's exactly what this shows. And then at this last point, it says V equals 0, meaning it's not moving, meaning it doesn't have kinetic energy. It also doesn't have any height. It only has elastic potential energy. The answer has to be A for number 14. I'm assuming some of you didn't see this V is greater than 0 or didn't pay attention to that arrow or something, but you should have selected answer choice A. All right. Number 15. My last class, this was also one of the most missed questions. Let's see. This was your most missed question. 70% of you got it right, which as far as most missed questions go, that's not bad. 70%'s a pretty good percentage, but obviously this was one that if you missed something, it was probably this. That was the one that y'all struggled with the most. It says, a 0.025 kilogram paper cup falls from rest off the edge of a tabletop 0.9 meters above the floor. If the cup is traveling 4 meters per second at the moment that it hits the floor, what is the magnitude of the work done by air resistance during the cup's fall? So, I know that I have a cup on a tabletop. I know that that cup is going to fall, and that right before it hits the floor, it's moving. And so I know that I have initially gravitational potential energy due to its height. And just that because it says it falls from rest. Okay, so I have GPE at the top. I know I have KE at the bottom, and those two should be equal to each other unless there's something like friction or air resistance, which is implied that there is in the question. In fact, I know that there is because there's no choice that says 0. So there is air resistance. Okay, the question is, how much work does it do? And so I could do this a couple different ways. I could simply solve for the gravitational potential energy, solve for the kinetic energy, see are they equal? If not, figure out how much energy was lost. Or you can build it into your equation by adding work to the formula that you're using. GPE plus work, it always goes on that left-hand side. That's the only way you're going to get the right sign. Okay, GPE plus work, it will be negative work if it's air resistance, equals KE. Okay, so let's go ahead and find that GPE. GPE is mass times gravity times height. That mass is 0.025. Gravity is 9.8. The height is 0.9. Okay, and then my kinetic energy over here, 1/2. The mass is again still 0.025. The velocity is 4. Are those equal? That's the question. Okay, so let's solve for each of them. 0.025 times 9.8 times 0.9. Again, you don't want to have a negative energy here. I know that the acceleration is negative, but your energy is scalar. Okay, so that's why we don't put the negative sign. But this is 0.2205. Is it equal to this? Let's find out. 0.5 times 0.025 times 4 squared is 16. This is 0.2. Nope, they're not equal. You could have just done that. Are they equal? No. Okay, let's figure out the difference. Okay, or if you have it built into the equation, you can figure out the difference that way. But it's the same thing. We're going to subtract 0.2205 from both sides. Okay, when we do, we're going to figure out that we have a negative amount of work, which we should, but here it only asks for the magnitude, so we don't have to worry about the negative sign. And the answer you should get once it's rounded anyway is A, 0.02 joules. Because you basically lost this 0.0205. It just rounded. Questions about number 15? As I said, that was your most missed question, so several of you struggled with it. All right. But most of you got it right, so again, it wasn't everybody. Number 16, which spring shown on the graph would be the tightest, requiring the most force to stretch it? In other words, which one has the greatest spring constant? Okay, we have an equation for spring constant. It is your spring force divided by the displacement of your spring. Okay, and in this graph, this is a force displacement graph. So guess what? That's rise over run. If all you have to do is find the slope. You could also pick points on the graph and read them. That works too. If I look at this, let's say I want to displace a spring 20 meters. Spring C doesn't take very much force, like maybe 3 newtons. Spring B takes like 15, and spring A takes, I don't know, 34. Okay, you can tell just by looking at a single point as well which one's going to take the most force to stretch. But ultimately it goes back to slope. Okay, whichever one has the greatest slope has the greatest spring constant and therefore requires the most force to stretch it. That is spring A. The answer to number 16 is A. Only one person missed that. Questions about number 16? All right, number 17. This was tied for your second most missed question, and it was also the most missed question in my last class. Number 17 says a horizontal force of 16 newtons is applied to pull a 6 kilogram box initially at rest a horizontal distance of 10 meters. The box's final velocity is 7 meters per second. What is the work done by friction while the box is moving? So, again, this is a scenario where we have this box that we know is moving at the end. We already know what happens at the end. It's moving. Okay, and the reason it's moving, it's not because it went down a hill. It's not because it was on a spring. It's because somebody pushed it. There was work done, or actually they pulled it. There was work done when this box was pulled. And so theoretically, the amount of work that was done to pull the box should be equal to the kinetic energy that the box has at the end, unless there's friction, which it says, what is the work done by friction? So they're implying, and by the way, there is no option of 0, so there was friction. Okay, I can solve for each of these and see are they equal, and then if they're not, figure out what the difference is, or I can build it into my equation. That work done by pulling the box, well, guess what? There's also work done by friction. It's going to be negative work. Sometimes this equation is just written, in fact, usually it's just written like this: net force equals KE. And I could do that, but my net force is the sum of my forces. Okay, so if I want to do this, let's go ahead and figure out how much work was done by the pull and how much KE we have at the end. So the work done by the pull applied to the box, again, work is force times displacement. They tell me the force is 16. They tell me the displacement of the box is 10. Okay, is that equal to the kinetic energy it has at the end? 1/2 times that mass, it says, is 6, times my velocity squared, that's 7 squared. Okay, so if we want to solve for this, this is going to be 160. Over here, this is equal to 147. Okay, those are not equal, which means that we had to have lost some energy. There had to have been negative work done. How much? Well, you can find the difference. Or if you just write it in your equation, you're already set up to solve for it. Subtract 160 from both sides. That's going to tell you what your work is. It's going to be a negative number. It's supposed to be a negative number. Okay, you're losing energy from the system. The work is removing some of that energy. And so you get an answer of negative 13, which is answer choice A. Are there questions about number 17? You could also have set this up to have dissipated energy instead of work done by friction. I don't know if that is more or easier or harder for y'all. But again, if you want, just solve for the before and the after and see if they equal each other. If they don't, subtract, and then check your sign afterward. All right, last one is number 18. It is graphs, which I know are y'all's favorite, but you have seen these graphs before. In your notes, I had graphs for every single relationship up there. I would very strongly encourage you to look at those again. I would not be surprised if it shows up on your test. Okay, so you might want to go back and look at the notes. This question says, an object is thrown straight upward. Which graph best represents the relationship between the object's potential energy and the height of the object above its release point? So you're really looking at the relationship described by this equation. GPE is mgh. So what is the relationship between height and GPE? Because that's what's on the graph. And it is a directly proportional relationship. As the height increases, so does the GPE, and it does so linearly. It should be a straight line, okay, because it is a directly proportional relationship. If this doubles, this doubles. If this triples, this triples. If it's half, that's half. Okay, and so the graph that shows that is graph B. That should be what you selected for number 18, and 85% of you got that one right. So y'all did pretty good with it. But again, I would strongly encourage you to look back at those graphs. All right, so that is it as far as the multiple choice goes on our quiz. However, you know that your test is going to have a free response question as well. And what we decided to do is we're going to give you 2 free response questions tomorrow, and you're going to pick one of them. Okay, so you have a choice. So if you're trying to review for that, you're going to have a choice that's going to involve something where we did some examples in the MyOpen Math where you had, some energy calculation to get a box moving or a ball rolling, and then there was a collision afterward, that type of question. Where it like goes down a ramp, how fast is it moving at the bottom? Okay, now it's going to hit this. You've seen some like that. In fact, we did a warm-up the other day like that, except we're not going to worry about the projectile motion part of it. Okay, so there's not going to be a projectile in that calculation, but something that looks like that. Okay, and then the other option is going to be more of just the energy stuff, energy and work stuff. So kind of like the question that we just calculated here, or like if you look back at MyOpen Math, like the skier on the hill, and it goes down and then back up, and it asks you like how fast they're moving, that type of thing. Okay, so depending on which one you feel more comfortable with, you'll have that choice tomorrow, but that's what you should expect for free response. Otherwise, the multiple choice, it probably looks pretty similar to what you just looked at today. They typically do. But you can also look back at your My Open Math stuff. Go back through that review if you didn't finish it, or even the problem sets. And then you also have a unit summary. If you're looking for additional practice, you've already done all the My Open Math and you want to look at something else, try that out. But again, you do have a test tomorrow. Please make sure that you study for it. And then if you haven't turned in your RA, please make sure that you're getting that taken care of as well. If you guys have any questions for me before you leave, please make sure you ask. Otherwise, you can come in for tutorials after school today. They will be in either on Thursdays, either in Miss Torres's room or in Mr. Guthrie's room right next door.